Hello friends, this is Kamal Sarma. Welcome to my class, and today I am going to discuss about the capacity of a section for bending moments, shear force, axial forces or torsion, etc. and the required strength the structure need to have because of the external loads. Okay, I will discuss about the external loads also. What are the loads that is applied to the structures? I discussed a little bit about that in my first video, but today if time permits, I'll go a little ahead of that, what I have said on that day. But first of all, you have to look at what is the design procedure we use for finding out the capacity of a section. There are two different procedures we use actually. One is the old, the other one is a new one. The old one is called working stress design or allowable stress design. The newer one is called the limit state design or load and resistance factor design. The philosophy is almost the same, but the limit state design or load and resistance factor design is somewhat more practical, more realistic. Okay, so let us see what if I can explain it that the way I can show you the easiest way. Okay, now say Rn is nominal capacity. Nominal capacity. Why Rn is nominal capacity? Because we directly take the value of Fy. This is yield stress of steel. You might be considering that we use concrete also as a structure, but remember, steel is also part of a reinforced concrete, and in most cases it is recommended that we should design the concrete beam under reinforced. That means the steel should attain the yield stress before the concrete gets it. That means concrete, before the concrete collapse, it should yield. Okay, that is the meaning. Yielding means, then what happens, you probably know, when the steel yields, the failure you can see a little bit yielding like that, a little bit bending like that, there will be cracking on that, a little bit. So then you know that the beam is failing. It will give you time to escape. But if the concrete fails, it's a brittle failure. If the compression is so much that the failure is sudden, you have not had any time to get out for safety. So that is the reason all the steel concrete sections are to be designed for as a under reinforced. That means you will provide less rebar, reinforcing bar, than actually it is required for a balanced section. Okay, that is the meaning. And in structural steel also, structural steel mean if you use beams like that or angle section, these are structural steel member, rolled steel, or you can use the plate girder also. They are structural steel. It has got only one yield stress, Fy. But what is yield stress? You probably know that if you have stress strain curve, you might have seen in your classroom. It is somewhat like, it goes like this. You start at 0, then this is almost like a straight line. The stress is proportional to strain. After that, it yields a little bit, then come down, then again go up, and like this. This is the maximum. This point somewhere here, it is called yield point, Fy. I will explain this with a good figure next time or class after that. Okay, so this is a Fy. We want to make sure that it doesn't, this structure doesn't attain the Fy, the yield stress. Okay, so it will be somewhere here or there. But this is the limit step. It cannot go beyond Fy, yield stress. Okay, so what happens? Our N is moment capacity or shear capacity or torsional or axial capacity, keeping in view that we are considering as if it is failing at Fy. Then what happens in working stress design? You divide it by factor of safety. This is the nominal capacity, now it is factor of safety. If you divide, it becomes not a nominal, now it becomes the capacity of the section against any forces, moments, shear, axial, whatever you call it. This is the capacity now. So Rn divided by factor of safety is the capacity by working stress design. Working stress or allowable stress. They both are same. Okay? But there is another method I already told you, the limit state design. Limit state design. That means it is close to the limiting condition Fy and or load and resistance factor design. This is the capacity you get for working stress design. For working stress design. For limit state design, this value is the nominal capacity. This is the nominal capacity Rn. We are multiplying with a resistance factor. Phi or phi. In United States it's called phi. In India probably it is called phi. Same thing. It is a resistance factor. This is the total, it is the capacity. Again, this whole thing is the capacity. In working stress, the factor of safety for axial, that means tensile force, axial tensile, 1.67. If you have a, that means it becomes your 0.6 Rn. It is almost similar. You see, 0.6 Rn. But in the right side, the required strength. What is required strength? That comes from the, where I told you in my earlier classes, that because of the external loads, the internal forces develop. Those internal forces are moment or bending moment, shear force, axial force. This has got two. One is tension or tensile, and other one is compressive. And last one, 1, 2, 3, 4, last one is torsion. These are the 4 forces that develops within the member because of the external force. I will talk about the external force. Okay? So these are the forces developed here. So this is your capacity. Phi Rn is the capacity by limit state design or capacity of the section. Moment, shear, torsion, axial force, it doesn't matter. It's just, this is a generalized symbol. This is a generalized symbol. Of course, this is not 0.6 for everywhere, but you can say it is written as a lambda. This is a factor of safety. So this is the working stress. But this capacity of the section should be greater than the required strength. Required strength with external loads applies some bending, shear, axial forces. So it develops some stresses or whatever the forces, tension. That value of the design should be greater than the required design. Required design for the forces due to external forces. That means the design, it is something like that. I equal to 1 to I. It is called gamma I R or Q. Okay, this is for, and this is not for, there is no gamma term. So it is I equal to 1 to I, Q, and I. This is the required strength to counteract with the exterior forces. I will tell the what are the external force? It's the dead load, the live load. I will explain each of them. I told you a little bit about that. Then, and combination of all the forces, say wind load, earthquake load, then you have a snow load in the snowy area, where suppose in the Himalayan region or in United States, northern part of United States or Canada or Europe, all these places you need to consider the snow load, SL. Besides that, some other loads also there. If you design something under soil, it will call substructure. Suppose that if you have something under the soil, suppose a footing or abutment, whatever it is, there we have to consider the earth load also. So it is called earth pressure or earth load. Then we have all kinds of different kinds of loads. Okay. So these are the loads that will be coming to the structure, and because of this will develop. This is the required strength, minimum, that is the maximum required strength because of this, all this, and this is the minimum capacity. So this should be greater than that. Okay, so why I call it maximum? Because there is a reason. That is, you can see it here. Lambda I, Q, and I. We multiply this value. Earlier, in working stress, we do not multiply. As is, we are taking it. Whatever value we get, that is it. But the limit state design or load and resistance factor design, this is called load factor. This is your resistance factor. So because of these two, the design itself is known as load and resistance factor design. This is mostly commonly used term in United States. But India probably people mostly use limit state. I don't know that part, but I think that is the case. Anyway, here you do not multiply the load, whatever external load you find, and because of that, a required strength is, you have to compare with the capacity of the section, and the capacity should be greater than that. At least it should be equal. It is not recommended. It should be always greater than that. That is my personal view. Okay. So here also this is the case. Mathematically it is the case, but better you should have it greater than that. So Rn, this is the capacity, and this is the required strength. Required strength. This required strength is needed to counteract the external forces. And what happens? Why this gamma I go 1 to I? This is called load combination. That means it is something like that. Gamma I, Qni, this is for dead load. Plus gamma 2, Qn and 2 for live load. This is for live load. If you consider a snow load also, you can add another thing, gamma 3, and your Q and 3, it is for snow load. So that means you are multiplying this gamma with it for the dead load design strength, live load design strength, but these values are different. They may be equal, but not necessarily they will be equal. In India, this is called load combination. We apply this different load combination for the design purpose to see the worst case. So here one load combination is 1.5 for Q and 1 dead load plus 1.5 for live load plus 1.5 Q snow load. So, but when snow is not there, you don't have to consider. This is one combination. There are other combinations also. Okay? But here working stress, you don't do any multiplication. You simply say it is dead load, Q for dead load, Q for dead load, Q for live load, Q for snow load, like that. Do not multiply. But almost it is same, because why? See what happens. If you 1.5, 1.5, so you take 1.5 common, this is for here. 1.5, 1.5, this is 1.5, this is 1.5. If you take common, so it is dead load, Q dead load plus Q live load. You remember Q is required strength. So 1.5 this side, it is say 0.9 Rn. Actually, the Q value varies. It is always these phi values. Beg your pardon. This phi value or phi value is always greater than 1. Always greater than equal to 1. And load factor most like is commonly it is I beg your pardon, I made a mistake, sorry. Phi value is less than 1, less than equal to 1. It cannot be greater than 1. And phi, this gamma value is greater than equal to 1 in both cases. Sometimes it may be less to have the worst effect. I will discuss about that later. But phi is always less than or equal to 1. It cannot be greater than 1. I get confused a little bit, sorry about that. But here the gamma value is, in most cases, is 1. So here gamma is 1.5, phi is 0.9, say. For tension it is 0.9. So if 0.9 divided by 1.5, you get 0.6. Okay? Remember here, if you divide by Rm equal 1.67, this becomes 0.6 R of N. So these both, if you bring it to the other side, it becomes 0.6 Rn equal to almost same working stress and design stress at this for this case. But it is not always true because our gamma value not always 1.5. It depends on the uncertainty of the load. Okay? In United States, in one combination, the gamma is 1.4 when you take only dead load. But in other cases, if you go with live load, it is 1.2 dead load plus 1.6 live load. See? Not same, 1.5 like that. So depending on how uncertain about the load, dead load is easily calculated because you know the dead load is self-weight of the structure or load coming from anything permanent that is attached to the structure. That means if you have a beam, you know the dead load of this, weight of this from the cross section. You know that this depth and breadth, you multiply that, and this length L. So that is D times L is the volume, and you multiply with the load per unit volume. That will be your total weight. So that is the dead load. But one thing is that this load is uniform. So this load for W, you have to divide it by L. So it is uniformly distributed. We show it with a cloud. Or sometimes people show the uniformly distributed load, something like rectangle with arrows down. Like that, small arrows, okay, uniformly distributed. So this is the dead load. So in no case the section will change. So dead load more or less is certain what the dead load is coming. Suppose it is, if you have a slab is there is transferring the load to the beam underneath. So I told you that there's a tributary area like that. So this part of load will come in to the beam. Something like that. If you draw the beam here, this is a trapezoidal road because of this trapezium. I will explain why we consider this way later. It's a long process of telling things. There are so many small things. If you are new to structural engineering, probably you get confused what I am talking about. But you have a little bit of background, probably you understand. This is the load coming like that. Trapezoidal load. So these dimensions are same. So your dead load is certainly whatever it is there. So it is certain. No uncertainty is there. But live load, it may vary. You do not know. I have seen one lady in India. Her top floor is full of tubs. Flower tubs, vegetable tubs, all this. The designer did not know she will be putting so much live load there. Okay? So this is the problem. People misuse the structure sometimes. They put extra dumb stuff there. You do not know as a designer. So in bridges it is worse. Sometimes the heavy trucks comes with 4-wheeler, 6-wheeler, 7-wheeler, 14-wheeler. They put more loads to the bridge. So in bridges, this live load is 1.75. More uncertain. This is in United States. This is the case. And for bridges, this is 1.25 dead load. You see, I am putting an I after L live load. This I is actually impact factor. Because when a truck goes, it not goes smoothly, right? It vibrates. It goes over. There's a bump there, there's a dip there. So because of that, it vibrates, right? The weight of the truck, weight of the vehicle put some impact on the bridge. That impact factor, whatever is there, live load by that is equal to 33%. 33% increase of this. So actually this becomes LL. So this whole thing is 1.75 times 1.33 LL, live load. Or you can write it this way. Nowadays it is 33%, but 0.33. Earlier it was, you calculated some equation there, it may be less than 0.3 or 3 also. But nowadays it is called dynamic load coefficient or something like that. It's impact factor. Okay? So now you know what is design strength and required strength. So design strength, again I am writing the formula for allowable stress. It is your Rn divided by omega is greater than equal to I equal to 1 to I Q and I. This is for the different loads. And in LRFD, load and resistance factor, LRFD, we call it LRFD, load and resistance factor design or limit state. This value is Rn phi value which is less than 1, maximum 1, equal to or greater than gamma I Q and I. This is when we study, this was not there. LRD design. We knew only the working stress design. Allowable stress design or now today you know that all we design, we have limitation. We cannot go beyond yield stress. We cannot go beyond yield stress. You should be below the yield stress so that the structure remains safe. Okay, we'll discuss more about that in next class. And this is the design philosophy or of limit state design. There is no magic number like that. They find out individually. Depending on the uncertainty of the load, that this value is varied. It may have a different value, but it is not the same. But in some cases they may be same, but not necessarily. And one thing you already know, you know that the loads are acted together. It is not like dead load will act one time, the live load will one time. These loads are mostly the natural loads coming from the self weight, the permanently attached something to the structure, or depending on the use of the structure, whatever purpose you use the building or the bridges. For bridge it is the vehicle load, and the loads coming from nature. Okay, something like wind load, earthquake load, snow load, all loads. So the structure should be safe. I told you earlier that because of the external loads, the internal forces develop: moment, shear, torsion, axial, compression and tension. And that should be counteracted by the structure, by the design with the capacity. Capacity is more than the required strength. That's it. That's all for today. And I appreciate for attending my class. And my advice to you: listen to it, watch it, try to understand it. If you have any problem, if you do not understand, write in the comment box, or if those who are friend with my Facebook, they can ask me directly. Thank you very much. I appreciate it. See you next time. Bye.